Welcome! Today, we're going to dive deep into a word you probably use every single day, work. You might feel like you're doing a ton of work studying for an exam, but to a physicist, you might not be doing any work at all. So let's break down the real and honestly kind of surprising meaning of work in the world of physics.
All right, here's our game plan. First, we're going to separate the everyday idea of work from the strict physics definition. Then we'll get into the simple formula behind it and see how work can actually be positive, negative, or even zero. After that, we'll connect it all to the huge concept of energy. And finally, we'll see why this one idea is so crucial for, well, understanding how the universe ticks.
Okay, let's jump right in. The number one rule for understanding work in physics, you gotta forget what you think the word means. Seriously, in science, the definition is super specific, and the two concepts are, well, they're not even in the same ballpark. So let's kick things off with a classic physics brain teaser. Picture this. You're holding a really heavy bag of groceries, and you're walking at a steady pace across a room. Your arm is getting tired, right? You feel like you're putting in effort. But here's the question. From a physics perspective, are you doing any work on the bag itself? Just think about that for a second.
And this is the official physics definition. See, work is only done when a force actually causes an object to move. You absolutely need both ingredients, a force, a push or a pull, and a displacement, which is just a fancy word for movement. If you've got one but not the other, then nope, no work is being done. At its heart, work is really just the process of transferring energy.
So how do we actually calculate this thing? Well, it turns out those two key ingredients, force and displacement, come together in a formula that's both super simple and incredibly powerful.
This image pretty much sums it up perfectly. To do any work, you need a force that results in movement. I mean, think about it. You could push against a brick wall with all your strength. You'll get tired, you'll sweat, but if that wall doesn't budge, you've done exactly 0 joules of work on it.
And here it is, the math in its simplest form. Work equals force times displacement. That's it. We measure work in a unit called the joule. And just to give you a sense of scale, 1 joule is a tiny amount of energy. It's about the work it takes to lift a small apple about 3 feet off the ground.
Let's make this a bit more real. Say you push a box with a force of 10 newtons. That's about the force it takes to hold up a 2-pound bag of sugar, and you move it for 2 meters. You've just done 20 joules of work. See? Simple multiplication.
Okay, so that was the easy example, where you're pushing something straight forward. But, the universe is a little more complex than that. What happens when your force and the object's movement aren't in the exact same direction? Now this is where it starts to get really interesting.
And that brings us to the different flavors of work. Positive, negative, and yes, even 0. It all comes down to the angle between the force you're applying and the direction the object is actually moving. So we've got to update our formula just a little bit. Now, don't let the math freak you out. This cosine of theta part is just a really clever way of figuring out how much of your force is actually helping out in the direction of motion. It's just a number between 1 and -1, and it's the magic key that tells us if we're adding energy, taking it away, or doing nothing at all.
Now what's so cool about this is how it lays it all out. If you push in the same direction something is moving, the angle is 0 degrees and the work is positive. You're adding energy to the system. If your force is fighting the motion like friction does, the angle is 180 degrees and the work is negative. You're taking energy away. And right there, that's the answer to our little puzzle from the beginning. When you carry a bag, you're pulling up to fight gravity, but you're moving forward. That's a 90-degree angle, and the cosine of 90 is 0. So you're doing absolutely 0 work on that bag.
So just to recap, there are 3 main ways you can end up with 0 work. 1, nothing moves, like with our friend the brick wall. 2, your force is perpendicular to the motion, like when you're carrying that heavy bag. And 3, all the forces on an object canceled each other out, so there's no change in its motion. Okay, so we've established that work is all about transferring energy. And this isn't just some vague idea. It's a core principle in physics called the work-energy theorem. Let's take a look at how they connect mathematically. What the theorem says is actually pretty elegant. The total, or net work you do on something, is exactly equal to the change in its kinetic energy. And kinetic energy is just the energy of motion. So basically, doing work on an object directly changes its speed. And of course, physics has a really nice, clean way of writing this out. W net equals delta K. The net work equals the change in kinetic energy. It means that every bit of work you put into an object shows up directly as a change in its motion. It's a perfect one-to-one relationship. And if we unpack that change in energy part, this is what it looks like. You're just calculating the object's kinetic energy after you've done the work and then subtracting the kinetic energy it had before. That difference? It's exactly equal to the work you either put in or took out.
So here's the bottom line. If you do positive net work, you're adding kinetic energy, and the object speeds up. If you do negative net work, like the work that friction does, you're removing kinetic energy, and the object slows down. It's like a perfect energy accounting system.
Okay, so why did we spend all this time completely redefining a simple, everyday word? Because understanding work in the physics sense is the absolute key to understanding everything about energy. Work is how the universe moves energy around. It's the physical process that connects a force to a change in motion. The work done by the expanding gas in a car engine is what makes the car go. The constant work done by gravity on a planet is what pulls it into an orbit. It's the same fundamental principle at play, from a tiny engine all the way up to an entire solar system. And this really flips the perspective perfectly. If work is the act of transferring energy, then energy itself is just the ability to do that work. The two are completely intertwined. One is the doing, and the other is the potential to do.
So I'll leave you with this question. Now that you've seen the world through this new lens where work is the transfer of energy, how does that change what you see around you? When you see the wind turning a turbine or an apple falling from a tree, you're not just seeing movement anymore. You're seeing work being done. You're seeing energy on the move. What else are you going to start noticing differently?